All right, in this video, what I want to do is go over some of the properties that matrices have. This is material from section 2.2. And so rather than write all this out, just because this is kind of a longer list, I have pre-written this out and I just want to talk about them. So here, capital A, B, and capital C are matrices. Lowercase c and d are scalars, which for now just means real numbers. We won't need to use capital C as a matrix and little c as a scalar in the same line, fortunately. So this should all be pretty clear what I mean. So a few properties that matrices have in common with the real numbers, and these are all properties that are true for the real numbers as well. The first is that if you add two matrices, it doesn't matter the order. So we say that addition is commutative. If we add three or more matrices, so this is a capital C. If we add three or more matrices together, it doesn't matter the order. So we can add the first two together first or the last two together first. It doesn't matter. We have associativity of scalar multiplication. So if you have C times dA, that's the same as CD times A. You have a distributive property. There's a few distributive properties, but the first one is that if C is a scalar and A and B are matrices, then you can distribute and you get CA plus CB. So that looks pretty natural. Likewise, you could have a sum of two scalars and then distribute against a matrix. So that this would be CA plus DA. So this is all perfectly unsurprising so far. Not much really to talk about there. Now, when we're talking about multiplication, multiplication is associative. So if you multiply three or more matrices, it doesn't matter where you put parentheses, as long as you have them in the right order, the product will be the same. There's two distributive properties for matrices. So if you were to multiply on the left by matrix A, and you were to multiply that by B plus C, across an addition sign, you would end up with AB plus AC. The one thing that I want to point out here, and the one thing that's important, is notice that the order matters for matrix multiplication. So I have this written down here, but notice that A times B and B times A are not the same. So you need to keep track of the order. The reason I bring that up is that for number 7, if you multiply on the left by A, so if you multiply A on the left of B plus C, then A goes on the left after you distribute. Okay, so that's important. So if A is on the left to begin with, then A is on the right after you distribute. Likewise, if you have A plus B times C and C is on the right, then after you distribute, C is still on the right. So you have to keep track of the order that you're multiplying the matrices in order for these distributive properties to hold. The last one is kind of a generic associativity property. It says that if you have a product A times B and you multiply that by some scalar C, you can put the scalar basically wherever you want. You can multiply A times B first, put the scalar in front. You could multiply C by A and then multiply that by B, or you could even move the C in and multiply that by B first and then by A. So that's just kind of a generic associativity property. A few things that are different with matrices than real numbers. One we've already seen before, and that's that matrix multiplication is not necessarily commutative. There are some matrices that when you multiply, they're commutative. The order doesn't matter. In general, for most matrices, the order multiplication does matter. A times B is not B times A for most matrices. Likewise, you don't have a cancellation property. So in real numbers, if you have, say, whatever, AX equals, so think about this just in terms of real numbers. If you were to have AX equals BX, in real numbers, that would imply that A equals B if X is not 0. Why do we have to exclude X equals 0? Well, it turns out that we have to exclude the case where there's no multiplicative inverse. And the same is going to be true here. We'll talk more about this property as we go along, and we get into, in the next video or two, we'll get into some matrix algebra. So those are the big properties that matrices have. And that's really all I wanted to say about the properties. There's a few other special matrices that I think are worth mentioning. There's the multiplicative identity, which we talked about before. So the multiplicative identity is the n by n identity matrix. So I'm going to write it I sub n. So this is going to be a square, meaning an n by n matrix, same number of rows and columns. And the way that this matrix will work is that you have a 1 along the main diagonal. I need to do this backwards because you're looking at it backwards, but it's 1 along the main diagonal and zeros everywhere else. Okay, so that's the multiplicative identity. And if A is an n by n matrix, then it turns out that when you multiply A by the identity, that's the same as multiplying the identity by A. And that's, of course, just A. The reason we call it the multiplicative identity is that it plays the role that 1 plays in the real number, so that when you multiply anything by 1, it stays the same. Likewise, if you multiply any matrix by the multiplicative identity, it stays the same. You get A. So that's the multiplicative identity, which we've talked about. One thing that I have not talked about is the additive identity. And so the additive identity matrix, otherwise known as the zero matrix, is the matrix that's literally all zeros. Usually we put a subscript mn, so it's a 0 subscript mn, and this is really zeros all the way through. Okay, so that's the zero matrix. If A is an m by n matrix, then it turns out that A plus 0 is the same as 0 plus A, forgot the subscript, which is A. Sometimes we don't use the subscript, so sometimes I might not put it in. But this is the additive identity because this is the matrix, so that if you were to add it to any other matrix, you get what you started with. This plays the role that 0 plays in the real numbers. Okay, so that's the multiplicative identity and the additive identity. A few other things just to talk about, a few other properties. If A is an n by n matrix, let me say this a little better. Let n be an n by n matrix. And if A has an inverse, so if A has an inverse, then the inverse is unique. There can be only one inverse if it exists at all. So matrices have at most one inverse. And a few other things just to think about. Powers of matrices, so this is worth talking about. If I were to write A cubed, it's probably clear what that means, but I just want to spell this out. This means A times A times A. It's the product of A with itself 3 times. Okay, so whenever you cube something, you're multiplying it by itself 3 times, no big deal. If I were to have A cubed, so let's say A inverse is the inverse of A. What is the inverse? So what is the inverse of A cubed? Well, there's a few different ways to think about this. So this is our question. So what's the inverse of A cubed if A inverse is the inverse of A? So in other words, if A has a non-zero determinant, so that A inverse exists. So A cubed is going to have an inverse, and you can write it as A inverse cubed, or because these are the same thing, you can just write it as A to the minus 3. It turns out that the inverse of A cubed is just going to be A inverse times A inverse times A inverse. And let's just check that this actually works. So if I were to take A cubed, I want to figure out what's the matrix so that when we multiply A cubed by that matrix, we get the identity. And it turns out that it's A inverse cubed. And that's because if we were to multiply by A inverse, what we could do is we could group the inner two matrices together And then we know that A times A inverse is the identity. So this is A times the identity times A inverse times A inverse. And say A times the identity is just A, and then we do it again. Notice that I'm trying to follow very strictly the rules that we have of associativity, definition of inverses, and so on. So A times A inverse, here I'm using associativity with multiplication. I can put the parentheses wherever I want. This is the identity times A inverse, and then A times the identity is just A. And then when all is said and done, this is the identity matrix. So it turns out that having negative integer negative powers of a matrix is a well-defined operation as long as the matrix has an inverse. Okay, so A to the negative 3 makes sense there. All right.